Hello, and welcome to our pre-calculus lesson today on rational functions. We studied polynomials, and polynomials were functions that you might think of them as normal. When you graph them, you get just nice smooth curves. There's no gaps, no jumps. Well, rational functions are built by making a ratio out of two polynomials. Now, you don't think of one, the function y equals 1 is a polynomial, but it kind of is in this case, in the consideration we're making here. It only has a constant term. So a most basic rational function is this y equals 1 over x. And right here, in y equals 1 over x, what we're doing is we're showing you a graph. This is actually one of the basic graphs that you should know. So what you see here is when x is positive, y is positive. That's because 1 is always a positive number. And when you do 1 divided by any positive value of x, you get a positive number. When x gets really small, when x is small, sorry, I'm having technology issues here. X is small, you get y is big. So over here, on the left side, you notice x's are negative on the left side. We know that, and y is negative. So when you do positive 1 divided by a negative x, you get a negative value for y. You should know this shape, but the interesting thing to look at is the domain of this function. You can't have zeros in the denominator. So the domain of this says x cannot be 0. And look what happens at 0. It looks like we might have a function there, but actually what happens is these y values get really, really, really close to x being 0, but never really get there coming from the left. Coming from the right, they get really, really, really big, but the y's get big, but you never actually cross that line where x is 0, otherwise known as the y-axis. This y-axis is something we call a vertical asymptote. Here, the x-axis, when you divide 1 divided by any positive number, you never actually get 0, but boy, does this look like it's coming close to 0, to y equals 0. And the same thing over here, 1 divided by a big negative x gets you a slightly little tiny negative number, but it's never 0. The fact that this function as x goes to positive infinity and as x goes to negative infinity kind of levels off to y equals 0. Y equals 0 is what we call a horizontal asymptote. And we're going to see these terms more, and x equals 0 is what we call a vertical asymptote here. And I will write the word asymptote out if I can learn how to use this pen. Asymptote. All right, there we go. There's a vertical asymptote. So I just wanted you to get an idea of what we're looking at. Now this graph of y equals 1 over x absolutely has to be known. You have to recognize that as 1 over x because we are going to work with shifting this one. Okay? So after we do that, here's the graph of y equals 1 over x squared. Now the only way this really differs, it's a little steeper because x squared, when you divide, it gets small when x is less than 1. So you're dividing by smaller numbers than you were with x, and it gets big quicker when x is positive. But what also happens is 1 divided by x squared, oh, that's interesting. I didn't know I could do that. I didn't mean to do that, sorry. X squared is always a positive number. So what you see over here is that when you do a positive 1 divided by a positive number, you get a positive number. So this is a mirror image left and right. Now this y-axis doesn't go to the same value as this one does, but this is 1 over x squared. So this also has a horizontal asymptote at y equals 0. It seems to level off to 0. If you had huge numbers for x, either negative or positive, if you had a number close to negative infinity, your y would be about 0, but it wouldn't actually be 0. Or if you had an x about equal to infinity, your y would be about 0, but not 0. So we say that's a horizontal asymptote. And I'm just going to write horizontal asymptote here. Again, you have a domain issue. X can't be 0, or you're doing 1 divided by 0. So you actually don't ever, if you follow the y-axis all the way up to positive infinity, you would actually never have either side of this curve cross this. It never actually touches the y-axis. It has no y-intercept. So this vertical line, y equals 0, is a vertical asymptote. So that's the idea of what a horizontal and vertical asymptote is. So let's move on to the next. I'll get better at the technology as time goes on, okay? Let's make sure that, I'll make sure that happens. Here is another graph. Okay, so this one kind of looks like 1 over x, but not quite. There's a couple of things different about it. And what I want you to look at is I'd like you to look at, first of all, what goes on here? All right? It does this diving off thing like 1 over x did. Well, it turns out this equation is y equals x plus 2 over x minus 3. So what happens is you see that x equals 3 is a bad thing, because you'd be, if x was 3, you get 3 minus 3 would be divided by 0. So x can't be 3. That's the domain of this function. And we'll go through step by step how you find domain and all these characteristics, but I just want to explain to you physically what they look like on a graph. So here's x equals 3. So what happens is if I draw a line at x equals 3, if I could draw a line at x equals 3, and I should use a different color here, you see this graph never crosses there. X equals 3 is what we call a vertical asymptote. Now, x plus 2, that doesn't bother the domain, but where x plus 2 equals 0, it's possibly where you cross the x-axis, and in this case it is. It's x equals negative 2 is the 0 of this function. And this function, because these top and bottom both have the same degree, it turns out, and this will be explained in more detail, both this levels off, but it doesn't level off to 0. It turns off, it levels off to, there's like a 1 in front of this x and a 1. If you put in a really big x, you will get y equals 1. And if you put in a really big negative x, you will also get y equals 1. So y equals 1 would be the horizontal asymptote. So we're going to look at finding these characteristics using the equations, okay? So I'm just going to show you a couple more graphs so you get the idea. All right, oh, here's another graph. This is kind of fancier. So this graph is in some ways similar to the function we had before. This function is y equals x minus 3 times x plus 7. That's a plus. Over x plus 2. So again, I have a domain issue in this one at x equals negative 2, because that is right here. That's x equals negative, oh sorry, these are in 2s, 2, 4, 6, 8, 10. So this is x equals negative 2. And what you would see if you went high enough up is you really don't ever cross that line at x equals negative 2. You have a vertical asymptote there. Let me see if I can get a different color pen to work. There we go. So this line at x equals negative 2 is what we call a vertical asymptote. It's a 0 of the bottom. It might be, this is related to the domain. You might be starting to see that. Now, x minus 3 would be 0 at x equals 3. And what we see happens at x equals 3 is our graph crosses the x-axis. X plus 7 would be 0 at x equals negative 7. And look at this, at negative 7, we cross the x-axis. So, you know, the other way I could write this one out, if it weren't factored form, let me erase this. If I don't want to have it in factored form, this would become x squared plus 4x minus 21. So in order to find out those two things I just found over the 3 and negative 7, I would have to factor this. I would have to use the quadratic formula to find the zeros of the top or some way. But we'll go through those techniques. So there's another type of graph you might see that's called a rational function. Ooh, this one's really fancy. So for this one, I've got all kinds of stuff going on. It looks like I got something going on here. I got a couple of vertical asymptotes, it looks like. And no, I didn't talk about horizontal asymptotes, but it certainly looks like this is going to level off to something out here, and it's going to level off to the same thing out there. But let's just look at this equation. The last one we saw had no horizontal asymptote, by the way. Let me just scroll back to that. This graph here, there was no horizontal asymptote. That's not going to level off. You can see this is going way off that way. This one's going way off that way. It has end behavior. Turns out the end behavior, look at this, x squared divided by x, that would give you an x. The end behavior is just like the end behavior of the function y equals x. If the top degree is higher than the bottom, you actually don't get a horizontal asymptote. I'll go through those rules later. But here's another function that is a rational function. And this one actually is, I kind of kept adding to this. This is x minus 3 times x plus 7. Same top as our other one, as our previous one a moment ago. And then I added something to the bottom. I still have that x plus 2 on the bottom, but then I have x minus 5. And what you'll see is I've got vertical asymptotes at -2, because that's what makes x plus 2 0, at 5. So the two holes in the domain are where my vertical asymptotes are. There's a vertical asymptote at 5, going up and down that way, and a vertical asymptote at -2. If I drew that line, y equals -2 is x equals -2 and x equals +5 are vertical asymptotes. And look, I cross the x-axis at x equals 3, which is a 0 of that, and x equals -7. So the zeros at the top can give me the x-axis, the x-intercepts, and the zeros at the bottom give me not only what can't be in the domain, but also where these vertical asymptotes are. So here is another function. It looks a little simpler, but I want to show you I've only changed one thing from the last function, and that is I've changed that x minus 5 to an x minus 3. So this function is y equals x minus 3 times x plus 7 over x plus 2 times x minus 3. And what you see here is you only have one horizontal asymptote, and it's at x equals -2. I mean, one vertical asymptote. You would expect to see one at x equals 3, but you don't see one. It looks like x equals 3 is just fine and dandy, although you know it can't be in the domain. Turns out this graph doesn't show you there's actually a little hole there. Now, the reason the 3 is not a vertical asymptote is because it's also a 0 of the top. And notice it's also not an x-intercept. The only x-intercept happens at x equals -7. So what we're going to do in this analysis is find the zeros of the top and the bottom. The zeros of the bottom are going to tell us something. The zeros of the top are going to tell us something. But the ones that are any numbers that are both zeros of the top or the bottom, they create what we call a hole. It tells us something else. So the first thing we do is list all the zeros of the top function and all the zeros of the bottom function. Then we go through a process of using that to find vertical asymptotes, x-intercepts, and holes. So that first piece of analysis where you find the zeros of both the numerator and the denominator will give you 3 pieces of information right away. Horizontal asymptotes is a separate process, but it's not difficult. It has to do with comparing the degree of the top and the bottom, and there's only 3 ways it can turn out. So I'd like you to use this as an overview, get an idea what these graphs look like, and we're going to go on. There's going to be 2 more videos. One will talk about the step-by-step process for finding domain, vertical asymptotes, x-intercepts, and holes, and then the other one will be the step-by-step process for finding horizontal asymptotes. Okay, thank you, and we'll see you again soon.